All right, so when we were, as I've been watching people take multiple choice uh, extra credits, there's a type of problem that continues to show up that people struggle with. So we're going to take a look at three of them, and then we're going to do an FRQ that's related to it. So two friends, Andy and Bob, participate in games of bowling every week. From past experience, it's known that both friends' scores are approximately normally distributed, where Andy has a mean of 150 and a standard deviation of 30. And Bob has a mean score of 165 and a standard deviation of 15. Assume their scores are independent. That's important. Otherwise, we can't do the problem. Which of the values is closest to the probability that Andy will have a greater score than Bob in a single game? We see that Andy typically loses, but we want to know, hey, when might Andy win? Well, first off, Andy typically loses by 15. So we combine the two together, and we can do that with means directly. And we find out that Andy's losing by about 15 points. To start winning, he has to cross over 0. So I'm looking for this part over here where it's greater than 0. And by the way, I just subtracted those directly. Fact of the matter is, I can't do that with my standard deviations, but I can sum them and take the square root of them. So now I have a lower bound, an upper bound, a mean, and a standard deviation. So I could do a norm, CDF, lower bound is 0, upper bound, infinity, mean of negative 15, and standard deviation of whatever that mess is. So here we go. Second vars, normal, CDF, lower bound is 0, upper bound 9 caret, 9. Mean of negative 15, and a standard deviation of 30 squared plus 15 squared raised to the half power. So about 33% of the time. About 33% of the time. Sean and Evan are college roommates who have part-time jobs as servers at restaurants. They work in food services. The distribution of Sean's weekly income is approximately normal with a mean of 225. So Sean, 225 mean, and a standard deviation of 25. The distribution of Evan's weekly income is approximately normal. And he has 240 with a standard deviation of 15. Which of the following is closest to the probability that Sean will have a greater income than Evan in a randomly selected week? So once again, we subtract. And once again, they're very creative. And Sean is making $15 less than Evan. Well, he doesn't make more until he crosses 0. So I'm looking for this. Once again, I can't subtract them, so I can only add them. So I have 25 squared plus 15 squared for my standard deviation. So once again, we're looking for a norm, CDF, lower is 0, upper, infinity, mean, negative 15, and standard deviation of 25 squared plus 15 squared. All right, so let's do that. Second vars, normal CDF, lower is 0, upper 9 caret 99, negative 15, and standard deviation of, clear that, parenthesis 25 squared plus 15 squared, close parenthesis, raised to the half power. And we get 0.303. So very, very similar to the problem above, but I thought doing 2 of them would be helpful. Actually, we're going to do 3 of them. Now, this is very similar to what we just did, but they changed it up because the others weren't hard enough, so they had to make it a little trickier because that's who they are. So 2 college roommates have committed to donating to charity each week for the next year. The roommates' weekly incomes are independent of each other. Suppose the amount donated in a week by one roommate is approximately normal with a mean of 30. And I'm going to call it roommate 1 and roommate 2 because they didn't give me names. So mean of 30 and a standard deviation of 10. The other roommate donates 60 with a standard deviation of 20. Which of the following is closest to the expected number of weeks in a 52-week year that the donation will exceed 120? Well, 30 plus 60 equals 90. All right. So what we're expecting is, on average, they give $90. But we want to know the likelihood that they give over 120. Well, I can't add them directly, but I can square them to get my standard deviation. So now I have a norm CDF of lower 120, upper positive infinity, mean of 90, and standard deviation of 10 squared plus 20 squared. So let's do that real quickly. Second var is normal CDF. And we have a lower bound of 120, an upper bound of that, a mean of 90, and a standard deviation of 20 squared plus 10 squared. I guess I changed the order, but and then raised to the half power. Now, what I'm calculating here is a probability. So my probability that it's greater than 120 equals 0.089. .0898. They didn't ask me for the probability. They asked for the expected number. So the expected number, expected value is n times p. Well, we have our p, and it's like, oh, my n is 52 because I have 52 weeks. So 52 times 0.0898. And I end up getting 4.67, which is the closest value there is 5 weeks. So we're going to continue with the combining of the random variables and figuring probability out. So there are 4 runners on the new high school team. The team is planning to participate in a race in which each runner runs a mile. The team time is the sum of the individual times. So we're going to sum these times for the 4 runners. Assume that the individual times of the 4 runners are all independent of each other. Again, if they're not independent, we can sum the means, but not the standard deviations. So super important. The individual times and minutes of the runners are in similar races are approximately normally distributed with the following means and standard deviation. Runner 3 thinks that he can run a mile in less than 4.2 minutes in the next race. Is this likely to happen? So what we need to be looking at is we're looking for the probability that x is less than 4.2. Well, we know the mean, we know the standard deviation. So and his value is 4.2. The mean is 4.5. Oops. Yeah, I'm sorry, I had the wrong runner, runner 3. Runner 3 is 4.5. So 4.2 minus 4.5 was a standard deviation of 0.14. And I end up getting a z-score of negative 0.2. And all I have to do this, and if I were drawing the picture of it, and it really helps. And not only that, sometimes it'll get you some credit. You have 4.5 here, and you have a 4.2 here, and we're looking for the likelihood that it's something less than 4.2. So to run this thing, I'm going to go second bars, normal, CDF, lower bound, -9.99, upper bound, 4.2, mean, 4.5, standard deviation of 0.14. Now, the problem with doing this is I get the probability nice, but I don't get the z-test. So probably a better way is to go stat test, and this is a z-test because we know the population standard deviation. So if I go to stat test z-test and I plug in as 4.5 for the mean, the standard deviation of 0.14, the x of 4.2, and then it asks for the sample size. Well, our sample size is 1 because we only want to run one race. And there we go. We get our z statistic and our p-value. So the question is this likely? And the answer goes, it's possible, but there's only 1 per 6 cents chance of it happening. So it's not likely. And you have to have that statement as well. So not only show the math, but say possible, probably not going to happen. All right, the distribution of possible team times is approximately normal. What's the mean and standard deviation? Well, the means I can add up directly. So I just do, boom. So in this case, we expect it to take 18.9 minutes. And I'd love to add up the standard deviations, but I can't do it directly. I have to square them and sum them. So there they are. They're squared and summed, and I end up with a group mean of 0.3003. So now they say, suppose the team's best time to date is 18.4 minutes. What's the probability the team will beat its own best time? Well, we expect it to be 18.9. We want to know the likelihood is going to be less than 18.4. So that's what we're looking for, is to negative infinity. So once again, I plug in. And in this case, I'm still going to go stat test z-test. My mean is 18.9. My standard deviation is the 0.3003. My x is 18.4. And my sample size is still 1 because it's one team. It's not the 4 individuals. We're talking about one team because we're talking about the time for one team. We end up getting a z-score negative 1.6. So there's about a 0.047. There's about a 4.79% chance that they'll beat their own best. Possible, not real likely, but more likely than the bragger.